Next, I will talk about how we compile this NIZK to an OR proof. For simplicity, I will first talk about how we achieve the OR proof for 1 out of 2 disjunction. In this construction, the prover wants to prove that for 2 matrices M0 and M1 and 2 statements X0 and X1, there exists some J which is 0 or 1 and some witness W such that Xj is equal to MJW. The CRS is the same as before. And to generate the proof, the prover first split the original CRS R into a binding CRS Rj and a hiding CRS R1 minus J, such that the sum of these 2 CRS is equal to the original one. And the trapdoor of the hiding CRS is T prime. Then the prover generates the proofs for Xj and X1 minus J with W and T prime respectively by making use of the prover and the simulator of the NIZK for the linear languages we talked about before. The Soundness follows from that when the parity of R is 1, then either R0 and R1 has parity 1, which means that one of them must be binding. And the zero knowledge follows from that when the parity of R is 0, then both R0 and R1 will have parity 0, which means that both of them will be hiding. To convert this OR proof to an OR proof for 1 out of n disjunction, the natural idea is just to split the CRS in a more general way. At first, assuming the jth statement is true, at first we let the prover to split the original binding CRS R into n CRS such that the sum of them is equal to the original one, and only the jth CRS has the parity being 1. And the verifier will check whether the sum of all the CRS is equal to the original one. However, none of them can be performed in AC0. So our solution is to propose a double layer sampler to sample n CRS with the sum being R. And this sampler can be run in AC0. At the first layer, we just sample n trapdoors with the sum being a 0 vector. This can be easily done by sampling n bit strings with the parity being 0. Next, in the second layer, we just sample n hiding CRS, which are random vectors in the span of E. We will sample these vectors by making use of the trapdoors we talked about before. And now we can obtain n hiding CRS with the sum being 0. And next, we will add the jth CRS with the original CRS, which is R. And now we obtain n random CRS with the sum being R and the jth CRS being binding. And we can see that this sampler allows a prover to split the original CRS into n CRS, satisfying our requirement in AC0. And we also need an additional step for verification. Specifically, we use the NIZK for linear languages to prove that the sum of all the split CRS is equal to the original one. And by making use of this proof, the verifier can check the validity of the split CRS in AC0, since our NIZK for linear languages can be run in AC0. Here we need an AC0 extractor, which can extract the witness from the n trapdoors we talked about before. And I will skip the details in this talk. Please see our paper for the details. Next, I will talk about how we convert this OR proof for multiple disjunction to the NIZK for AC0 circuit satisfiability. In our construction, the prover takes as input the witness and the statement circuit, which is in AC0. And it first extends the witness to contain the bits of all wires. If the witness is valid, then the output must be 1. And then the prover encodes each wire Wi as a random vector CTI with the parity being Wi. We can see that CTI is in the form that of E times Ri plus the lowercase e times Wi, and Ri is just some random vector. And for each unbounded flying AND gate, we just use the or proof for multiple disjunction to prove that either CTI minus E is in the span of E for some for all I, or CTJ and CTN plus one, which is the encoding for the output, are in the span of E for some J. And this is enough to ensure the consistency of the encoded wires. Here, there is a challenge that to get the witness, the prover has to decide which wire corresponds to 0 when the output is 0. And we can see that the prover cannot find such wire by searching each wire in order. Otherwise, the complexity will go beyond AC0. So we prove the existence of an AC0 algorithm that can output the index of the first 0 bit or 1 bit amongst n bits. And please see our paper for the details of the construction of this algorithm. And for the OR gates, we can prove the consistency in a similar way. And for the NOT gates, we just prove that the sum of E, the lowercase e, and the input and output encodings of the gate are in the span of E. So this is how we get the target construction of our NIZK. And we can also extend our NIZK to the non-interactive ZAPs, which are the which just mean the NIW in the plane model. To achieve this conversion, we just prove that our NIZKs have the verifiable correlated key generation, and with this property, we can just use the GOS conversion technique to transform our NIZK to non-interactive ZAPs. And we can also convert our NIZKs to ones in the URS model. For doing this, we can just see that a random vector is a binding CRS and hiding a CRS with the half-half probability. And by running our NIZK with the random CRS in parallel, we can just achieve our NIZK in the URS model. The zero knowledge of the resulting NIZK just follows from that of the underlying NIZK in the CRS model, and the statistical soundness just follows from that. For many random strings, at least one should be binding with overwhelming probability. So this is how we get the conversion. And this is the conclusion of our work. We proposed fine-grained proof systems that are unconditionally secure against AC0 adversaries, and all of them can be run in AC0. The proof system includes NIZKs for AC0 circuit satisfiability, non-interactive ZAPs, and NIZKs in the URS model. Thank you. That's all.
Question? Just great talk. A quick question about how you sample in the OR composition construction. You said you sample T of these vectors that sum to 0. They have to be sparse, right? So how exactly do you sample those in AC0? N vectors that sum to 0?
Okay, let me see. So are you talking about these two distributions? Can you see the screen?
No, this is in your OR composition. This was in the OR composition construction. How you can't just split. You have to pick T1 through Tn. So
okay, I see. Actually, in the first step, we just sample n trapdoors, with the sum being a 0 vector. And this can be done in AC0 since we just make use of the D0 and D1, the D0 distribution we talked about before. And this is in AC0. And in the second layer, we just sample the NCRS by making use of the trapdoors we talked about before. And in this step, we just compute in ET1 to ETN. And since E is sparse, so the multiplication can be performed in AC0. So this step can also be done in AC0. And we will also add the J statement with R, which is the original CRS. And this step is also in AC0 since we just make an addition. So all of the steps can be done in AC0. And of course, we should also generate the proof of the NIZK for linear languages. And in this case, we have to extract a witness that can be used to prove that the sum of the split CRS is equal to the original one. And we can also do this by making use of the n trapdoors we sampled in the first layer. So basically, all the multiplications just involves the matrix E, which is sparse, and a random vector. So all of them can be computed in AC0.
That's the question. Wait, but is there any question? From Zoom? No question. So let's thank the speaker again.
Thanks.
The next talk is triply adaptive using NIZK by Concatenated, Pratik Sakar, Xiaowan, and Pratik will give the talk.
Hi, can you hear me?
Yes.
Okay, cool.
So you can start whenever you're ready.
Yeah, I'm ready. Okay, hi, my name is Pratik, and today I'm going to talk about triply adaptive using NIZK. So this is a joint work with Concatenated and Xiaowan. So I will first briefly introduce NIZK. So in a non-interactive zero knowledge, there's a prover P who has inputs NP statement X and the witness W, and the verifier has the same NP statement X, and they also have access to a setup which is a CRS, and then the prover computes a proof pi, attesting the fact that X is in the language L and W is a valid witness. So correctness says that if X is in the language and W is valid, then verifier outputs 1. Soundness says that if X is not in the language, then the verified output 0 with high probability. And then we have non-adaptive zero knowledge, which is as follows. So here the simulator first samples a CRS and the trapdoor, and the verifier obtains this CRS. The verifier has an NP statement, and the simulator also has an NP statement, and the simulator comes up with a simulated proof, and it sends the simulated proof to the verifier. And non-adaptive zero knowledge says that this simulated proof should be indistinguishable from a real proof. And then this is the non-interactive zero knowledge that we know. It satisfies these properties. So we introduce the notion of triply adaptive NIZK, which adds 3 additional properties on top of the previous properties. Mainly, we require adaptive soundness, adaptive zero knowledge, and adaptive security. So let me define these properties, and then I'm going to talk why they are interesting. So adaptive soundness, there's a challenger who samples the CRS and provides it to the prover, and the corrupt prover now samples an NP statement and the proof to the challenger. And adaptive soundness says that if X is not in the language, then the challenger should output 0 with high probability, where the challenger runs the verified algorithm on the NP statement chosen by the prover and the proof. And note that adaptive soundness is stronger than regular soundness. In fact, the Groth-Ostrovsky-Sahai or the GOS paper is sound, but not adaptively sound. Then we have adaptive zero knowledge, where the simulator samples the CRS and trapdoor, and it sends the CRS to the corrupt verifier. Now the verifier comes up with a samples X and W in the language after obtaining the CRS, and it sends the statement X to the simulator. So the statement X is adaptively chosen based on the CRS distribution. Now the simulator again computes a simulated proof and sends it to the corrupt verifier. And adaptive zero knowledge says that this simulated proof should be indistinguishable from a real proof, even though the statement is adaptively chosen based on the CRS. So this is adaptive zero knowledge. And finally, we need adaptive security against adaptive corruptions. So here, suppose initially the prover is honest, and the simulator again samples the CRS and trapdoor. Now the verifier obtains the CRS and again samples the NP statement X and W in the language. and sends a statement to the simulator. Now the simulator comes up with a simulated proof similar to the zero knowledge game and sends the simulated proof to the verifier. But now, suppose the prover gets adaptively corrupted after the protocol execution. In such a situation, the simulator has to come up with a randomness which is consistent with the witness W and the simulated proof. So security against adaptive corruption says that this simulated proof should be consistent with the witness, like the honest witness, and some randomness provided by the simulator. So if you have this indistinguishability, then you have security against adaptive corruption. So a triply adaptive NIZK is a type of NIZK which satisfies these three properties: adaptive soundness, adaptive zero knowledge, and adaptive security against corruption. That is, soundness and zero knowledge should hold even when the statements are chosen by the adversary based on the CRS distribution, and adaptive security is security against adaptive corruption of provers. So why is this interesting? Because this notion of triple adaptivity provides realistic security guarantees. Here, the prover can basically use the same CRS to prove adaptively chosen statements. And we need security against adaptive corruption because this is very useful for real-life MPC protocols, where you are going to plug in your NIZK protocol inside a bigger MPC protocol. And finally, we also extend our NIZK to obtain UC security, and we also extend it to the reusable CRS model so that you can use the same CRS across multiple sessions between different parties. So this part is done using standard techniques from the literature. So let me now briefly describe the state of the art and how they compare with our main result. So the first work on adaptively secure NIZK was initiated by Groth Ostrowski Sahai, the GOS paper. So they constructed from pairings. They obtained adaptive security and adaptive zero knowledge, but they failed to get adaptive soundness. In fact, they obtained a weaker notion of soundness called adaptive culpable soundness because the real and ideal world CRS is just computationally indistinguishable because they are in the dual mode CRS setting. And then there was this work by Katsumata, who extended the GOS work for compact NIZK. They also achieved similar notions of security in terms of triple adaptivity, and they're also based on pairings. And then there was a work by Abe and Fer. So they constructed the first triply adaptive NIZKs, and their protocol relied on knowledge assumptions. So our task is to obtain triple adaptivity from standard notions where we don't need knowledge assumptions. Then there's a recent line of work which is based on correlation intractable hash functions. So this has been started by Kennedy et al., Piket et al., and Brzezinski et al. So they obtain adaptive soundness and adaptive zero knowledge, and they can instantiate their NIZK from LWE or DDH plus LPN. However, they fail to achieve adaptive security corruption. So our work is the first one which obtains triple adaptive security, and we obtain it from LWE and DDH plus LPN assumption. And we are also in the CI-based domain. So let's see some of the challenges and ideas. So our protocol is in the correlation intractable hash function based protocol domain. So the CI-based protocols actually require the interactive protocol to be statistically sound so that you can apply the CI argument. However, this contradicts adaptive security, as in security against adaptive corruptions, since a statistically sound protocol cannot be equivocated upon adaptive corruption. Also, previous adaptively secure protocols like GOS switch the CRS mode to perform equivocation. As a result, they only achieve non-adaptive soundness. So you cannot achieve adaptive soundness if you switch the mode of the CRS. So we overcome these problems. So by showing that you can apply Fiat-Shamir for interactive arguments instead of an interactive proof system. So we do this by relying on CI in the hybrids. And our underlying proof system is an argument. As a result, it's computationally binding and hence equivocal. And this allows us to get adaptive security corruption. And finally, we perform our soundness argument without switching the mode of the CRS. As a result, we obtain full adaptive soundness. And now let me formally define our contributions. So we first define a new non-interactive UC commitment functionality, which we denoted as FNICOM. So the current UC commitment, non-interactive UC commitment functionalities require interaction between the parties, even for like local commitment generation and verification. And that is very incompatible with MPC protocols. So we overcome that by introducing this non-interactive user commitment functionality. And here the parties can access the FNICOM locally for commitment verification, commitment generation and commitment verification. And our functionality also outputs the commitment string during the commit phase. So this models a non-interactive commitment more, and also it's very friendly to MPC protocols. And then we introduce the notion of triply adaptive Sigma protocol in the FNICOM model. And then we show how to compile such Sigma protocols to obtain triply adaptive NIZK by using correlation intractable hash functions. And inside this compilation, we are actually applying correlation intractability for NIZK arguments. And finally, we instantiate our compiler by showing that most Sigma protocols are triply adaptive in the FNICOM model. And finally, we implement the FNICOM with commitment scheme, with a Contenation commitment scheme. And we can implement our like these two instantiations from LWE or DDH plus LPN. And we can extend our protocol to obtain UC security using standard tricks from the literature. Now, let me briefly define this UC commitment functionality. So here the UC non-interactive commitment functionality is first initialized by the ideal world adversary with a simulation algorithm S. This algorithm is hard-coded inside the commitment functionality, and that helps us to generate commitment strings and verify. So now when a committer wants to commit to a message M, it invokes a commitment functionality with the message M, and it receives a commitment string C. And now the verifier obtains the string C from somewhere, maybe from an MPC protocol or directly from the prover, which we don't know. And now to verify, the verifier just needs to invoke the commitment functionality with the string C, and it obtains the output as 0 or 1, indicating verification has failed or verification has succeeded. And the verifier outputs the same bit. And we show that the Contenation commitment suffices to instantiate this commitment functionality. And if there exists an equivocal commitment scheme and a CCA2 secure public key encryption scheme with oblivious ciphertext sampling, then there exists a commitment scheme implementing this functionality. And we can build these from LWE or DDH. Now, let me define the notion of triply adaptive Sigma protocol in the FNICOM model. But before that, let me briefly talk about what is a Sigma protocol. So in a Sigma protocol, it's a public coin 3-round protocol where the prover computes the first message A, which mainly consists of commitments. And now the verifier samples a random challenge and sends it to the prover, and the prover computes the response and sends it to the verifier. And now it should satisfy correctness, and it should satisfy some property called special soundness. That is, if a correct prover outputs two accepting proofs, AEZ and AE prime Z prime, that is, for the same first message A, if the prover has computed two valid responses for two different challenges, then you can extract a valid witness from the transcripts, from the two accepting proofs. So this is special soundness. And then you require honest verifier zero knowledge, which says that there exists a simulator which, on obtaining a random challenge, can come up with a honest verifier zero knowledge proof, that is a simulated AEZ, which looks indistinguishable from a real proof. So this is the honest verifier zero knowledge. Now let me define the adaptively secure Sigma protocol in the FNICOM model. Here we assume that the prover and the verifier algorithm have access to the FNICOM functionality to compute this A and Z messages. So under the hood, it's like the prover can use the FNICOM to perform the commitments in A, and it can decommit it can compute the decommitments to Z and send it to the verifier, and the verifier can verify Z using the FNICOM. And now it should satisfy correctness and special soundness, same as the Sigma protocol. In addition, we also need the honest verifier zero knowledge. Here again, we assume that there exists a simulator algorithm denoted as sim1, which has access to the simulation algorithm of the commitment string, and it can compute as honest verifier zero knowledge proof. And we also require adaptive corruption security. That is, suppose the prover gets corrupted after the protocol execution, then there exists a simulator algorithm, sim2, which upon obtaining the witness and the randomness of the first simulator can come up with a randomness which is consistent with the simulated proof and the witness. So to summarize, this is the type of security that we need, adaptive secure HVZK. And this is the adaptively secure Sigma protocol in the FNICOM model. Now, the next step is to compile it to an adaptively secure NIZK. So we are going to do this by using the correlation intractable hash functions. So before that, let me show the Fiat-Shamir transform. So suppose you have a Sigma protocol. To make it a NIZK, you use a hash function H, where the prover computes the first message A, and then it computes the challenge E by applying the hash function H on the message A. And you can sometimes you can also compute parameterize this with the statement X, but here we don't need that. And then you send compute the response Z and send A and Z as the proof to the verifier. Now the verifier can recompute the challenge and then perform the Sigma verification. And now this hash function can be instantiated using a correlation intractable hash function. So what is a correlation intractable hash function? So a hash family H is called correlation intractable for a sparse relation R. If given a hash function H from the hash family, it is infeasible to find X such that X comma H of X is in the relation. That is for all probabilistically polynomial time adversaries A. It's infeasible to compute X such that X comma H of X is in the relation for a random hash function from the hash family. And for a function F, we denote the relation R of S as X comma F of X. So now we can replace the previous hash function with a CI hash for relation R pi, where R pi consists of A comma E such that there exists a Z where verifier accepts X, E, and Z. So this is the correlation intractable hash function. And these are like standard. This is like very standard from the CI based literature. And this NIZK again has to satisfy correctness and soundness. But here in the zero knowledge setting, we assume that the simulator samples the hash function in the ideal world. Now that was prelims for Fiat-Shamir. Now we are going to show our triply adaptively secure NIZK protocol. So our NIZK protocol is as follows. So we have the prover X comma W, and it will compute the first message alpha and also the response gamma. So let's see how it computes this alpha. So first it computes two transcripts, AC0 and Z0 and AC1 and Z1 for the same first message for two different prover chosen challenges, C0 not equal to C1. So it computes the two different transcripts for two different challenges for the same first message A, and then it commits to the challenges using the FNICOM, and it commits to the responses Z0 and Z1 using the FNICOM. Then it considers the first message alpha as A and the three commitments, and then it constructs a challenge by invoking the hash function on alpha. So the hash function is a CI hash for the relation RF, where F is the function where F of alpha is equal to 0 if and only if the verified algorithm on A, C0 and Z0 is equal to 1, where these C0 and Z0 are extracted from this alpha, that is from capital C and Z0, using the simulator algorithm of the commitment scheme. So as you can see, this S algorithm is inside the CI hash. And now you construct the challenge, and finally the prover can compute the response as by decommitting to the challenges C0 and C1, and also to the response ZE corresponding to the bit E and the decommitment to delta E. Now it sends. Now the prover is going to send this response alpha. I mean the first message alpha and the response gamma. And now the verifier is going to compute the challenge E by invoking the hash function. So this is going to be actually H of S. This is a typo. So this is the verifier is going to compute the challenge by invoking the same hash function on alpha. And now it's going to verify the decommitments to the two challenges and ZE in gamma. And it also has to verify that the two challenges are different. This is because we allow the prover to come up with the two challenges. So if the two challenges are same, then the prover can always consider the two challenges to be the same batch challenge. So as a result, we need two different challenges, and the verifier checks that over here. And then the verifier just runs a Sigma protocol verification on A, C, E, and ZE. And as you can, and so this is our NIZK compiler from a triply adaptive Sigma protocol. From a adaptively secure Sigma protocol to an adaptively secure NIZK. And we can also argue that if the Sigma protocol is triply adaptive, then it's the NIZK is triply adaptive. And the adaptive security and adaptive zero knowledge of the NIZK follows from adaptive security of the Sigma protocol in the FNICOM model. And soundness of the protocol relies on special soundness of Sigma protocol in FNICOM model and the correlation interactability for the RF relation. Also, the soundness of this protocol is half. And so regarding the CI, we argue CI inside the hybrids. So we first show that in the FNICOM model, these commitments are statistically binding. And then in the next hybrid, by relying on special soundness, we argue that the Sigma protocol transcript is statistically binding. And then in the final hybrid, we rely on the statistical CI to argue soundness. And the CI hash in our protocol is statistically, it's defined in the statistical mode in real world. So now let me talk about the instantiations. So we show that most Sigma protocols like Schnorr type protocols or the protocols in the Maurer framework are adaptively secure in the FNICOM model. The Gabel circuit based protocol of Hazai et al. Is also adaptively secure, and it avoids expensive CARP reductions. Even the protocols for graph Hamiltonicity are adaptively secure. And all of these can be implemented from LWE or DDH. And finally, we implement the kinetic fish link commitment and the equivocal commitments. Kinetic fish link commitment based on equivocal commitment and CC2 secure encryption scheme. And these can be instantiations from LWE or DDH. And note that for adaptive soundness, we need the CRS distribution of real and ideal world to be identical or statistically close for the commitment scheme. So to finally summarize our result, we proposed a new commitment functionality, which is more protocol friendly, and it has use cases beyond just NIZK. It can be useful for generic MPC. Then we proposed the definition and provide a generic compiler for adaptive for using NIZK with triple adaptivity. Then we instantiated the FNICOM from CF01, and we instantiated our NIZK compiler based on LWE or DDH plus LPN by instantiating the underlying CI hash. So if you can obtain more instantiations of CI hash, then you can obtain more instantiations of our NIZK compiler. For example, you can also instantiate our NIZK from sub-exponential DDH by relying on the state-of-the-art CI hash function from sub-exponential DDH. So that's all. Thank you.
Jan?
Hey, thanks for the great talk. And you said that the adaptive zero knowledge mainly came from the using NIZK, but it looks that in the paper you also state that the CI hash with programmability. So I wonder where this programmability of CI hash is needed.
Okay, so we need the programmability of the CI hash in the hybrids to argue we don't need it for simulation, we need it for the reduction in the zero knowledge setting. So that's fine.
And okay, and as far as I remember, this programmability of CI hash is kind of one time.
Mhm.
So, but it looks that you are reusing the CRS.
Right.
How is it possible to continue using the same CRS for many different theorems?
Right. So there are like a bunch of different transformations. So first we go from here to a short CRS model where we rely on the GOS result, and then we go to the result, like we make it UC compatible by relying on this special commitment called simulation sound trapdoor commitment. So we rely on that to move to that setting, right? And the CI hash is programmed only for the reduction. We don't need it for simulation. So it's fine in that way. Does that make sense? So to go from like single session to multi-session, you can use some simulation sound extractable commitment schemes, which is there in the GOS paper, and also some signatures like one-time signatures. So that's like a very standard technique to uplift to UC security. So that is there in the GOS paper, and also the paper by Ran Cohen and Abhishelat and Daniel Wicks. So yeah.
So time to move to the next talk. So let's thank the speaker again.
Thank you. Yeah.
Testing. Can you hear me?
So the next talk is efficient NIZK from LWE via polynomial reconstruction and MPC in the head by Paul Lowe, Reddy Gosar, Amit Sahai, and Paul is going to talk.
All right. Hi, I'm Paul, and this will be efficient NIZKs from LWE via polynomial reconstruction and MPC in the head. And this is joint work with Reddy Ghoshal and Amit Sahai. So our starting point is that prior to our work, all known NIZK arguments for NP from the hardness of learning with errors considered instantiating the Fiat-Shamir paradigm based on a parallel repetition of a public coin, honest verifier, zero knowledge, interactive proof. So and this is largely due to two works, CCH plus 19 and PS 19. So if you start with some NP language L and consider some statement X in the language, the way you would get a NIZK for L is first you'd apply the scarp reduction on your statement X to some NP complete language, such as graph Hamiltonicity. And the work of CCH plus 19 and PS 19 show us how to get a NIZK argument in the common random string model based off of some underlying protocol for Hamiltonicity, such as FLS 90. And the work of HLR 21 shows how to extend this to any commit in open protocol, such as the 3-coloring protocol for GMW 86. And in all these underlying protocols, you generally have a large proof size due to parallel repetition, which is performed to reduce the soundness error down to negligible. And in general, this carp reduction is computationally expensive, so you also have this overhead as well. And in our work, we give an efficient base NIZK construction for NP from LWE without parallel repetition and without carp reductions. And our tool of choice is MPC in the head, which was done by ICOS of 7. Let me know if there's like some fluctuation in the volume. Okay, and in particular, this allows us to translate work done on efficiently, perfectly robust MPC protocols, which exist from several works, to efficient NIZKs from LWE. You can think of our work as initiating the study of efficient NIZKs from the hardness of learning with error. And our main informal theorem is assuming the hardness of LWE. There exists NIZKs with computational soundness for all of NP, whose proof size is O of C plus Q times depth of C plus poly K field elements in some finite field F, where K is a security parameter, Q is quasi-linear, and the security parameter, the size of the field is as large as 2 times Q, and C is an arithmetic circuit for the NP verification function for some NP language L. And here what we mean by a base NIZK construction is that the work of GGI plus 15 show how to use fully homomorphic encryption to bootstrap an underlying NIZK to a NIZK whose proof size is effectively linear in the witness size. So you can think of our main theorem as providing a NIZK, a more efficient underlying NIZK from the hardness of learning with errors. As an overview of our technique, we're going to follow HLR21's coding theoretic approach to instantiating the Fiat-Shamir transform. And in particular, their work shows how to use list recoverable error correcting codes to address the case of exponentially many bad challenges, where the bad challenges have some product relation structure. And in this approach, the block size of this list recoverable error correcting code determines the efficiency of the proof. And here what we mean by efficiency, of course, is the proof size. And in particular, the list recoverable code they construct uses a Parvaresh-Vardy code concatenated with a single random code. And they achieve a block size of big O of K to the 1 plus epsilon for any small constant, positive constant epsilon. And you can ask, does the work of HLR21 generically apply to the setting of MPC in the head? And indeed it does, using the very specific properties of this Parvaresh-Vardy code. But we observe that this notion of general list recoverability doesn't take advantage of some structure that's actually present in the MPC in the head setting. And we can actually do much better. So we show that this yields less efficient proofs. And in our work, we observe that a modification of the original ICOS 07 protocol for MPC in the head allows us to use a strictly weaker notion of list recoverability, namely something we call recurrent list recoverability, which we'll define. And this allows us to use qualitatively simpler codes, namely Reed-Solomon codes concatenated with multiple random codes, and allows us to use aggregate size analysis and appeal to directly appeal to the polynomial reconstruction algorithm to achieve an improved block size of O tilde of K, so quasi-linear in K. All right, so let's do a review of MPC in the head from ICOS 07. You have a prover and a verifier. And the prover, you want to build a ZK protocol or a HVZK protocol. And the prover in her head imagines carrying out an MPC protocol for some function f sub L, which is really the MP verification function for some MP language L, where the input here is the statement X and a witness W, which I express here as Q secret shares with secret shares W sub I. And you can imagine Q parties who each get one share of the witness and the statement. And we say the view of this party is its inputs, its randomness, and its incoming messages, though without loss of generality, you can also think about including the messages it sends. And the prover will, in the first round, send a commitment to all these views. And note that these views also contain like randomness and inputs. And the verifier will then specify a random pair of parties, Pi, Pj. The prover will open to view I, view j. And the verifier will then just check the consistency of these views in the sense that the incoming messages and outgoing messages between these two views should be consistent. And this is a black box use of the MPC protocol. So let's unblack box this. So if we take a look at the view of, let's say, P1, who has input X, W1, and some randomness R, perhaps in the first round, the P1 sent message 1 to P2 and received message 2 from P3. for us to compute the next round's messages, namely the messages that P1 will send out, there's a deterministic next message function next, which takes in the identity of the party, 1 in this case, its inputs, X and W1, its randoms R, and all its previously received messages, because you can always just recompute all the sent messages from the received messages. And it computes all the next round messages that this party would send out. So here in round 3, the next function would say that P1 sends M3 to P2 and M4 to P3. And this allows us, this non-black boxing of the MPC protocol allows us to define a modification of the ICOS protocol, which will be important for how we instantiate Fiat-Shamir later on. In particular, what we're going to do is we're going to have the prover commit once to a transcript of the MPC protocol, including all the inputs and randomness. And now the verifier, instead of specifying a pair of parties, will just specify a single party P sub I. And the prover will open all the incident messages, the randomness, and the inputs for P sub I. And the verifier will now use this non-black box usage of the MPC protocol, in that it's going to use the next function itself to check the consistency of these messages. And to boost soundness, you can specify that the verifier instead specifies up to XC many random parties in some set S. And this will boost the soundness, and you can specify as much up to the robustness parameter of the MPC protocol. And of course, MPC-in-the-Head directly computes the MP verification circuit, so we avoid any CARP reductions. Here, it's not a parallel repetition. You only commit once to this transcript. And now each party's view is now independently verifiable, and this allows us to define a very clean bad challenge set structure, which I'll define in just a bit. So now here's how we're gonna follow HLR21's coding theoretic instantiation of Fiat-Shamir. So recall that how we're gonna recall this works. You're gonna start with an interactive proof for some MP language L, which satisfies completeness, statistical soundness, honest verifier, zero knowledge in a public coin property. And here you have the prover sending T rounds of messages, alpha 1 through alpha T, the verifier sending T rounds of challenges, beta 1 through beta T, and then there's openings gamma 1 through gamma T. And the Fiat-Shamir paradigm shows us how to compress this into a non-interactive protocol via some hash function H. And we would like that this usage of the hash function H preserves soundness to some degree. Namely, we can ask that it preserves computational soundness. And this happens if H is sampled from some correlation intractable hash family for an appropriate relation R. And what relation do we consider? We consider the following naive relation. For any statement not in the language, we want to consider all pairs of first round and second round messages for which there does not exist a opening that would convince the verifier to wrongly accept the membership of the statement. And these beta 1 through beta T's are what we call bad challenges. Namely, that these are challenges that would allow the prover to send a third round message that would fool the verifier into accepting the membership of the statement, which is not actually in the language. And the work of PS19 closes the case of this for using the hardness of LWE for the case of functions, namely circuits. And in particular, what I mean by that is if the relation is a function, meaning namely for every alpha 1 through alpha T, there's at most one bad challenge, beta 1 through beta T, then the work of PS19 addresses this case where we can instantiate a correlation intractable hash family for this relation from the hardness of LWE. And by guessing reduction, it also addresses the case of polynomially many bad challenges, where for every alpha 1 through alpha T first round message, there's only polynomially many beta 1 through beta T. And this is just by guessing, you incur polynomial loss by just guessing which of the tuples beta 1 through beta T is the one, is the correct one in some sense. But the moment you go to exponentially many bad challenges, you run into a problem because the guessing reduction will now fail. You'll incur an exponential loss. And the work of HLR21 says that for parallel repetition protocols, you have a nice product structure. So let's use this combinatorial structure to our advantage. So here's an alternate depiction of the exponentially bad challenge set. You just break it up into its T components, and each of these sets, so S1 is a set of all the beta ones, like the projections, basically. And these are all polynomial size sets. And what you would, applying the principle of wishful thinking, you would like that these T polynomial size sets define another polynomial size set, this pink shaded set, for which we could have another relation for which we could instantiate the previous slide's CI hash function for. So this is exactly list recovery, which is observed by HLR21. So this is kind of miraculous. And what we can do, therefore, is use list recoverable code and consider the following relation alpha 1 through alpha t and some r, and consider the relation where we just specify that the ith component of the encoding of r sits in the set Si. So this is a de-randomization this is a de-randomized relation, a relation for the de-randomized parallel repetition protocol. Okay. And in particular, what list recoverable code should we use? HLR21 says we can use Parvesh-Vardy code concatenated with a single random code. And let me tell you how this code concatenation works. You start with an algebraic code from some message space M to Z big Q to the T. And for when you send a message through, for every one of these T components, you're going to apply a random code on it. And this will give you, for each of these components, M Z little Q elements to get this, and therefore you get this code that goes from your message space M to Z little Q to the N, where N is M times T. And the list recovery just says that go the other way. You specify your sets S11 through S1M, apply list recovery to get some set S1, then apply this for all your T many random code recoveries, and then finally apply the list recovery for the algebraic code. And this gives you the set of all messages for which the code word sits in the the ijth component sits in the corresponding set. And HLR21 then showed this is a CI hash function for the desired relation. First, you have the PS19 CI hash for the encoding relation that we showed on the previous slide. Then you apply the list recoverable code. And just observe here that the block length of this list recoverable code affects the proof size. So here you start with the alpha 1 through alpha t's. After applying this new CI hash function, you get your beta 1 through beta t. And using a Parvesh-Vardy and single random code, you get a block size of size O to the K1 plus epsilon for epsilon greater than 0. And in general list recovery, you have to be worried on whether or not every one of these sets S1 through ST might be large. So you actually have to consider SI where SI may differ. And you may ask, is general list recoverability necessary for the setting of MPC in the head? And we actually observed that it's not necessary. Why is this the case? Well, in our modification of the ICOS protocol, we actually have a single bad challenge set, which is determined by this first round message commitment of tau, the commitment to the transcript, where scomp tau is just the set of all indices I for which UI is consistent, meaning that the prover could convince the verifier to accept incorrectly. So in the MPC in the head protocol, we just have product sets S cross S cross S cross S, and this critically uses the idea that we have independent verifiability for each of these parties specified by the verifier. And this is a much simpler structure, and we'll show how to exploit this simpler structure. Right, so one may ask, does a simpler batch challenge structure allow the usage of a de-randomization technique, both simpler and more efficient than general list recoverability? And the answer is yes. So here's a term we call recurrent list recoverability, a strictly weaker notion of general list recoverability, where instead of having arbitrary sets S11 through STM, you just have the same set reoccurring over and over again. And let's try to instantiate recurrent list recoverability with the simplest algebraic code we can think of. Let's just use the Reed-Solomon code. And we actually run into an issue for general list recoverability in the sense, or instantiating recurrent list recoverability in viewing it from the lens of general list recoverability, in the sense that list recoverability for a single code may result in an output set as tilde that's too large for the Reed-Solomon list recoverability. And for fixed random code, this happens with non-negligible probability over the prover's choice of S. It's not the verifier's choice, that's a typo. And in particular, to remedy this, we're going to make the following observation. The Reed-Solomon list decoding algorithm actually boils down to just polynomial reconstruction, which is a really simple algorithm given by Sudan 97 and Guruswamy Sudan 98. And polynomial reconstruction only relies on the aggregate list size, so the sum of all these S tildes. And we observe here that in the worst case, these S tildes could be as large as S times T, because a single set S tilde could be at least the size of, could be at least the size of S, because S could correspond to separate code words. Right, could just correspond to separate code words. So when you do list recovery, you'll get as many messages as the number of code words there are. And our solution is therefore to use multiple random codes. If you use multiple random codes, then while some output sets S tilde 1 might be large, others may be small. So you might have S tilde T be very small. And we show that in this regime, the sum of the S tilde i's is actually about, we get the cost of T many output lists for the cost of effectively 1. We get the sum of the S tilde i's is less than O tilde of just S. And this allows us to show that polynomial reconstruction succeeds for every choice of the set S with all but negligible probability. So in summary, we modified the MPC-in-the-Head protocol so that has a very nice bad challenge set structure, amenable to a strictly weaker notion of recurrent list recoverability. And we instantiate this recurrent list recoverable code using a Reed-Solomon code concatenated with multiple random codes. And finally, we show how to use aggregate size analysis to obtain something that's amenable to the polynomial reconstruction algorithm and achieves quasi-linear block length. And the final picture is effectively you take your PS19 hash, concatenated with a recurrent list recoverable code, which is actually Reed-Solomon plus multiple random codes. And finally, you get a reduced block length of just O tilde of K. And that's it. Thank you.
Any question? So I have one question.
Yeah.
So I think you give a efficient instantiation for Fiat-Shamir for MPC-in-the-Head, but if we don't care about the efficiency, is it easy to give a Fiat-Shamir for MPC-in-the-Head by using the existing work of HLR?
Yes. So if you don't care about efficiency, you can directly use HLR21. The MPC-in-the-Head paradigm falls under the commit and open protocol.
I see. Thank you.
Oh yeah. Yeah, I can hear you. Right.
The algebraic structure that you built.
Right. So this is, in a sense, we're using the work of PS19 and CCH plus 19 under the hood, right? Because
Underlying NIZK was you use FAQ for. That's the only LW.
oh no. So we don't use FHE. We just note that there's an additional work that bootstraps any NIZK protocol to another NIZK protocol using FHE, whose proof size is just linear in the witness size. So, but what our work shows is that we're not actually assuming the existence of a NIZK in the first place. We're building it from scratch. So this is a base construction.
Oh, okay.
Yeah.
I think I misunderstood that. Thank you.
Any other question? No question. So let's thank the speaker again. There's some announcement from time.